Hello, to those watching online, it is semester 1, 2025, and this is the revision seminar for the University of Adelaide course, Probability and Statistics. Yes, my last revision seminar for the season, so how exciting. There's still one more for Nicholas. So, yeah. I've had some requests, and my requests are these, and I might talk about well, maybe I'll start with the bit that I don't like, which is the Markov chains. So have you got that ready to go? Let me come have a look. Thank you. I'll pop this here for a sec. No, maybe what I'll do is take a photo of it. No, I'll just write it down. Okay, so so this was from assignment 5, question 3. So for the purposes of copyright, I did not write this assignment. That is this semester's course coordinator / lecturer. I don't know who that is, but that's who wrote it. So just so everyone knows that I didn't write it. So we have a machine that operates in 4 different modes. And it switches between the different modes through the following rules. 0 goes to 1 with probability 0.1. 0 goes to 2 with probability 0.2. 0 goes to 3 with probability 0.7. And if the machine is in one of the non-zero states, it always returns to state 0 the next time step. So if it's in 1 or 2 or 3, it always goes to 0 with probability 1. That's what that's saying? Okay. So xn equals state at time n, okay. Draw the state diagram, write down the transition matrix, and you're specifically interested in question part C, right? Assuming the machine starts in state 0, what is the probability that it will be in state 3 after 3 transitions? Prob in state 3 after 3 transitions. You should derive your answer by expressing the probability in correct notation and then applying the properties of Markov chains. Do not answer by multiplying the transition matrix, which seems like a bit of a waste of time to ask you what the transition matrix was, but whatever. And then it's got equilibrium probabilities, which wouldn't be the worst thing.
Yeah, that's
okay, that's the story. And so even though we are not interested in part A, I have to draw the diagram in order to process this. So we have state 0 and state 1 and state 2 and state 3. And these are all just 100%. And it goes to state 1 with 0.1 and state 2 with 0.2 and state 3 with 0.7. Okay. So it seems to me, with just thinking it vaguely about it, that if you left this machine running for a long time, if you looked at it at an even state, it would be in state 0. And if you looked at it in an odd state, odd time point, it would be most likely to be in state 3. Cool. This is a weird little Markov chain. Okay, so we may not be able to learn as much as we want to learn from this one because it's a weird little Markov chain, but that's okay. So, okay. So that's okay. I was just hoping that it said after 2 transitions, because then it's impossible to be in state 3, and that would be really easy. But no, okay, that's all right. So the rules of Markov chains are that the probability of going from state I to state J is independent of whatever state you were in earlier than that. It only matters what state you're in just now. Is that right? There's a word for it. Memoryless. Yeah. So the probability of being in state J, given that you're in state given all of the previous states, is the same as the probability of being of just the previous state. Is that how they write it? Maybe with equals as in all of them? Okay. Okay. All right. Okay, that's the main law of Markov chains, right? All right, just checking this is the... What's that? Time homogeneity? So that means that the probability of going from state, so this is probably, so that's the main law. And then there's the time homogeneity, which is saying that probability of getting from like, is the same as for any other time that are one apart. Yeah, for all M and N where this makes sense. Is that how they write it? What did they write? Okay. Like that? Ah, N plus 1 and N. Okay, cool, cool, cool. Probably doesn't matter exactly how you write it. For all N. Okay, cool, cool, cool. Right. So in general, though, most people who work on Markov chains just don't even worry. They just kind of have that implicitly in their mind. They just kind of ignore it. And they just do it as if it's there. Okay, cool, cool, cool. But if they want me to use proper probability notation, it feels to me like maybe they're going on this vibe. Okay. Okay, so I want the probability of being in state 3 given that state 0 was 0. That's the goal. Start in state 3, the probability that it's in state 3 after 3 transitions. Yep. And okay, so we can imagine all of the pathways that go from 0 to 3, and we have all of those probabilities involved. I don't know if this is useful at the moment, but at the moment I'm going, we can go here, here, and then here. You can go here, here, and then here, or we can go here, here, and then here. Right? Here. That's the only way things that could possibly happen, right? If it was 5, we could go here, 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 and then here, and here, 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 and then here. There's lots more options. Okay. So it looks like we're going to have 3 different probabilities added together. But just from the purposes of this will be the probability that x3 is 3, given that you were, was it in x3? No, x2. So 0 to 1, 1 to 2, 2 to, oh no, that's right. Plus probability that x3 equals 3, given that the previous one was 1, plus the probability that x3 is 3, given that the previous one was 2, plus the probability that x3 is 3, given that the previous one was 3. This is my thought about it. Like, you have to imagine all of the places it could have come from, theoretically, and combine those. So this is a law of total probability thing. There are x3 being 3 can happen in 4 different ways, depending on what the previous step was. So this is kind of like a probability of A is probability of A and B1, and the probability of have I done that wrong? Just give me a second. That's not a given, is it? Nope, I'm wrong. Sorry. This should be an intersection. There we go. That's better. Because this is the law of total probability, right? Yeah, the probability of a particular thing is what you get when you combine it with various different options for different options. And so I've done that. Okay, cool. So that's that rule. And then when you, I'm just going to come a little further away so that I can see both of these at the same time. Then the intersections are the probability of x3 equals 3. So this event happens if you go from x0 to x2 and then from x2 to x3. So this is x3 equals 3, given that x2 equals 0 and x0 equals 0 times the probability that x2 equals 0, given that x0 equals 0. Yep. Is that okay? So sorry, what's that? So this x0 equals 0 is part of the P at the moment. So this statement here has a given x0 equals 0, given x0 equals 0, given x0 equals 0, given x0 equals 0. And then we have that P, A, and B is the probability of first B happens and then A happens given that B happens. But this has a given x0, this has a given x0 equals 0, this has a given x0 equals 0. And when you combine two givens together, it's just a comma. And so all of these will be similar. Like that, and so on. Technically, I think you're allowed to skip straight from the original one to here. You don't have to do the middle one. Yep.
Prior to that, you just got rid of probability of x3 equals 3, except x3 1 and 2.
Yes, you could have. You could have given removed this here, but it's much easier to remove it here because you previously wrote that given x2, this probability was 0. So I'm just doing it the long way for myself. And then according to the Markov chain rule, this is just the same as this, and it doesn't matter whether x0 was 0. Blah, blah, blah. And now this is 0 because they told us that. Yeah? Because this was one of the original pieces of information they told me, which was the probability of 1, 2, 3 going to 0 is 1, and therefore the probability of 1, 2, 3 going to anything else must be 0. And so now these are 0. And so I get the probability that x3 equals 3, given that x2 is 0. Like that. And I know what this is. This is 0.7. So that's here from 0 to 3. And this one's going to have to be split up into its 3 pieces as well. So I'm going to have 0.7. That would be 0.7 times. So we could probably skip a bit of the working there and skip straight from the original, from here to here, like probably. But so we have x2 equals 0, given that x1 equals 0 and x0 equals 0 times probability that x1 equals 0, given that x0 equals 0. Yep. Because that's how that works. Plus probability that x2 equals 0, given that x1 equals 1 and x0 equals 0 times probability that x1 equals 1 and x0 equals 0. And so on. And this probability is the same as the one without the x0. And you know that this one's 0 and this one's 1 and this one's 1 and this one's 1. Yeah. One equals 3, given that x0 equals 0. And now we in fact have all of these probabilities told to us. So this is going from 0 to 0, which is 0. And this one's going from 1 to 0, which is 1. And this one's going from 0 to 1, which is 0.1. And this one's going from 2 to 0, which is 1. And this one's going from 0 to 2, which is 0.2. And this one's going from 3 to 0, which is 1. And this is going from 0 to 3, which is 0.7. And these three things add up to 1, and so we just get 0.7. Yay! Technically, I should have put one more line of working in here to declare that this is the same as without the x1, x0 equals 0. If I really want to do all of the probability notation. Yes, you could use summation notation. But there are only 3, so I felt. Yes, so. Yeah. Most of the time, they probably wouldn't want you to do the whole shebang, and they'd be okay with putting little PIJs. Yeah. So the kind of the short version is that, yeah, the probability of, yeah. So you could probably skip this bit because you know that it doesn't matter how far back it came from. But for the purposes of doing the probability notation, that's what that's about. Yes.
So in general, we have P of X given Y comma Z. We can turn that into P of X is Y times Y given Z. That.
Yes, let's just do it for a second. So that is P of X. So if it was just X given Y, this would be, right?
Yep.
Right. And then, bear with me. I did that back here, just a second. Where did it go? This one.
That one.
Yep. And then this is P of X given Y times P of Y, right? Oh, sake of a brown. How did I do it before? I had to concentrate so hard to do this.
So
It's okay. No, that's the wrong way around. Ignore that completely. So we know that P of no. So for Markov chains, no, this would be a division, right? It's the other way around. Bear with me. So we did this one here. Oh no, we created these intersections. They weren't there before. So we said there are 4 ways to be for x3 to b3, and that's for it to come from these things. So we created those intersections. It was this intersection that became this. So it was actually that the probability of x and y given z is the probability of x given y, but they're both given z. Like that. That's the rule. Yeah. So without the given z's, it's the traditional version of how you get intersection from a tree diagram.
Yeah.
You go to y first, and then you go from y to x. That produces x and y at the same time. And they're both given z, and so that given z just attaches to the given. Yeah. Yes. And I really do have to cover them up and do the normal one and then put the givens back in. That's takes some concentrating for me. Does that help to answer the question that you had originally? Yeah, if there's only 4 states, then you can just write it as a proper sum, like as an addition with pluses in them. Yeah, but you could have done it. We could just to make an attempt. We could have that P x3 equals 3, given that x0 equals 0, would be the sum from I equals 0 to 3 of the probability of x3 equals 3 and x2 equals I, given that x0 equals 0. That's what I wrote, but as with pluses. And so we have to say, we have to come from somewhere. And then this is this. Yes. And then this is and then all of these are 0 except 1. Except the one where I is 0. So this one is yeah. And then this one's a sum as well. No, but that's not a 0, that's a 0, right? Yeah. Okay. And so that neatly made it not a sum because most of them were 0. So they were trying to be nice to you. Yeah, since otherwise this is 0. And then you could go And then this one's equal to that without that. And then that one is 0. That one is 1. They're all 1, right? Ah, yes. One times px1 equals j, given that x0 equals 0. And if you're adding up all of the probabilities of coming out of x0, then they add up to 1. Because these are all the probabilities that came out of x0, so they must add to 1. Yay, okay, so that's you know, that's fine too. Total all probs given x0 equals 0 must be 1. And so we just get 0.7. Okay, so I can see how doing the sum notation version would work. Yeah?
So you scroll up button. So between the top one you've got there, how does the comma x0 service go on?
Because it's a Markov chain. And nothing before the previous state matters.
Ah. Right.
So if this wasn't a Markov chain, then that you couldn't do that. But because it is a Markov chain, nothing before the if you're looking at state 3 here, nothing before state 2 matters. Sorry? Ah, yes, queen. I was not processing what the word was. I thought you said hui. Okay. Okay. Rightio. So yeah, this point here was where we use the Markov chain rule. And technically we should have done it here too. We should have had an extra line in here to make this into the one without the x0. Being completely rigorous. Sweet. Are we okay with moving on to other kinds of things now? Okay. So out of our other requests on that one, moment generating functions and CDS versus transformation methods finding PDFs, which one do you want to talk about first? Okay. The person who commits gets the gets the thing. Moment generating function. Okay, so and I just checked, did they talk about probability generating functions in this course? Yeah. Did they talk about any other generating functions? Okay. Yeah, it happened like once for about 3 minutes. So when a mathematician says generating function, that is a function that in some sense will generate the thing that it's supposed to generate, but it may not generate them in the same way. So that doesn't mean anything I said there, but the point is that moment generating functions generate moments, and probability of generating functions generate probabilities, but they do them in their own separate ways. So in order to know what a moment generating function is, you do have to know what a moment is. And so if you have a random variable, y, then the nth moment of y is the expected value of y to the power of n. That's what they mean by a moment in this sense. Well, the first moment is the expected value. And the second moment is involved in the variance, the expected value of y squared. So the first moment is the expected value of y to the 1, which is just the expected value of y. And the second moment is the expected value of y squared, which is involved in the variance. And if the expected value of y is 0, like the normal distribution, the expected value of y squared is the variance. So that's useful to know. So, and then the third moment is, I don't know. It just turns out that if you know all the moments, then that will tell you exactly which distribution you've got. So, oh yes, it is. Yep. Just wait. I'm not talking about the moment generating function yet. I'm just talking about the moments. Know all the moments, and therefore you know the distribution. If you've ever studied physics as an engineer, I'm sure most of you haven't, in statics, which is a physics course of things that aren't moving, because they're static, they talk about moments there, and over in physics they call them torques. So, and they really are, in some sense, torques, because some people talk about the expected value as being the balance point of a distribution, where if you drew your distribution and you balance it on at the expected value, it would balance. There would be the same amount of weight distributed nearby to that point as on this side. And so in terms of the way physics works, there'd be, when you have a weight pushing at a distance, weights that are further away have a greater effect on the rotation. And so, which is why when my children were 3, I could balance them they could balance me on a seesaw if I sat very close to the center, and they sat very far away. And so when you calculate the expected value, you multiply the value by its probability, and that's kind of saying how far is this from the middle times probability, and it actually is calculating torques. So there you go. It's one of the reasons why they're called moments, is because they are torques. It is the location that you should put it to get 0 torque. Yeah, there you go. It's the torque around 0. Anyway, that may or may not help, but if you've done physics, it may help you. Okay. And so if you have done physics, then the expected value of y squared is like the moment of inertia. There you go. Why it's called a moment. And actually, a lot of our theory of probability distributions comes via physics, weirdly, because quantum. So, okay. This I've been told. I don't know the details, but yeah. Okay. So if you know all the moments, it's just one of those things. If you know the expected value of all of the powers of y, then it will tell you the distribution. And each distribution has its own list of moments. And if they're different at any point, then they are not the same distribution. But if every one of those things in the list is the same, then they are the same distribution. It's pretty cool. So here's the thing. I would like a function that in some way generates the moments. Okay, I'm going to see if I can figure this out from scratch. Bear with me. Pivot for a moment and think about just functions, functions have something similar to this, where you can write a function as a polynomial and have coefficients for 1 and x squared and x cubed and x to the 4 and x to the 5. And if all of those coefficients are the same, then it's the same function. That's called a Taylor series. So what I'm going to do is knowing, so we just aside, with functions, I can write f of x as a0 plus a1 x plus a2 x squared plus a3 x cubed plus blah, 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 right? And this is a Taylor series. And if two functions have the same list of coefficients, then they are in fact the same function. And that's very similar to my list of moments and being the same distribution. And in fact, the function I'm thinking of is the distribution probability density function. And so it's not exactly the same. So what if, crazy idea, what if I put the moments in these spots? Right? That'd be cool. But I'm not going to do that. I'm going to do this. What if I made a function and I put the moments in these spots? Like that. Because if you did a Taylor series, the AN is fn x on n factorial. Okay, I know it seems like a stupid and crazy thing to do, but the point is that two functions will be you can completely define a function by its list of coefficients here, and I can completely define a I'm going to call it m. I can completely define a probability density function, like a probability distribution by its list of these things as well. So what if I just combine those two ideas and said, I'm going to make a function by using this list as the coefficients of the things? That's the idea. Yep. And when I do that, this thing is the moment generating function. It generates the moments by them being part of the coefficients of this. These are t's now because they're not x's anymore. It generates the moments by those moments being coefficients in this Taylor series. That's the idea. And if I'm really lucky, I can know exactly what function this is the Taylor series of. So I just want to check something. Can you just check for me in the notes that the expected value of y to the power of n is the nth derivative of the moment generating function with 0 subbed in? Is that right? Right. So I have got this correct then. Okay. Right. So the reason why that is true is because this coefficient should have as its numerator the nth derivative of m with 0 subbed in. Like this. So we've set it up specially so that that happens. So the e y to the n on n factorial is the nth derivative of this with 0 subbed in on n factorial. And so ta-da, it works. It's just one of those clever things. Now, wait. This is the really, really cool part. You ready? Watch this. The Taylor series of e to the power of ty is 1 plus ty plus ty squared on 2 factorial plus ty cubed on 3 factorial plus and so on, right? Which is 1 plus ty plus y squared on 2 factorial t squared plus y cubed on 3 factorial t cubed plus whatever. And we're going to do the expected value of that. And when you do the expected value of things that are all added together, you can just do all the expected values separately. The expected value of 1 is 1. And the expected value of this, the t counts as a constant, so it will come out of the expected value. And the t squared counts as a constant, so it will come out of the expected value. And we'll get a 2 factorial, and we'll get a t cubed and a 3 factorial and an expected value of y cubed. And look, it's the moment generating function. Isn't that cute? So that is why we did it the way we did. Like, it's just, let's use what we know about Taylor series and what we know about expected values and make a magic trick that does this. I love it so much. So ultimately, that's what it's for. And so we have this thing. So we have that the moment generating function MGF for y is the function of t, which is the expected value of e to the power of ty. That's what it is. And it has the properties that the nth derivative with 0 subbed in comes out to the expected value of y to the n. But it has the secret extra property that I didn't tell you explicitly, which is that the Taylor series for it at 0 looks like that. Yep. Correct. You sub 0 in because that Taylor series that I just wrote there is centered at 0. This one that has like e1 plus x squared on 2 factorial plus x cubed on 3 factorial is centered at 0. It's technically a Maclaurin series. Yeah. But yes, you sub it into 0 because that is the Taylor series you're looking for. When you do the probability generating function, you sub in 1, I believe. Wow. If you sub in 0, something happens. If you sub in 1, something happens anyway. Probability generating function is not made the same way. It's made a whole different way. So, okay, and that is that. Isn't that fun? If you sub in, and there's always a 1 here, because y to the power of 0 is 1, and the expected value of y to the power of 0 is the expected value of 1, which is 1. Always a 1. Yeah, cool. And that is what they are. And the nice thing about them is that they tend to be neat little functions. Even though the Taylor series is what we're kind of in the back of our mind thinking of, we're thinking of this infinite list of moments. We can wrap up all of those moments by kind of un-Taylor seriesing it and getting a function. And we did that by doing this. And then each type of distribution has its own specific formula for what its moment generating function is. And if you have a moment generating function, you can look at it and go, oh, that's a normal distribution based entirely on its moment generating function instead of based on its PDF. And so we've now added a different way of telling which distribution we've got. So how to tell what distribution you have. We have one way, which is the PDF, classic. We have another one, which is the CDF. That's great too. And we also now have the list of moments, if you really want. No one will believe you with that one, but it's totally a truth. And you have the moment generating function. These are all now ways to tell which distribution you have. And it turns out for some distributions, the moment generating function is much easier than any other method for telling which distribution you have. Now, there are some ways to tell what your distribution isn't, which is finding its mean and its standard deviation, right? And if it has the wrong ones, then it's not the distribution you were thinking of. But just the mean and the standard deviation isn't enough to tell you which distribution you have. You need the entire list of moments. And the mean and the standard deviation are only involved in the first two moments. Yeah. There you go. And like, if, for example, if you have a probability distribution, and you want to know if that you haven't got a particular one, you can find the CDF at one specific spot. And if it's the wrong answer, then it's the wrong distribution. So yeah, but these are ways to tell. And we've just added this new one, new and improved way of telling whether things are the same distribution. And it's useful in my head to keep it this way, to say this is one of the ways to tell. So, for example, in the proof that when you add two normal distributions, what you still have is a normal distribution, that is usually done with moment generating functions. I believe also that if you square a normal distribution, then a standard normal distribution, then what you get is the chi-square distribution with 1 degree of freedom. That's also done with moment generating functions. Yeah. There is one other way to tell which distribution you have, which is to know what story it belongs with. I just want to add this. It's slightly dodgy. For example, if they said, we watched the sky for 3 hours and counted how many lightning strikes there were, and you go, oh, that story totally goes with the Poisson distribution. So just so you know. Yeah. But exactly which Poisson distribution would be to do with what the average number of strikes is and that sort of thing. But just that's the secret last one. Okay, so it's very difficult to find a moment generating function from scratch for some distributions. But let's do one, okay? So the moment generating function of the standard normal distribution. And I will call it Z because that's its traditional name. So the moment generating of Z, which is distributed according to a normal distribution with mean 0 and standard deviation 1. Okay. So the moment generating function for Z at t will be the expected value of e to the tz. And this being a continuous distribution, the expected value of e to the tz will be multiplying e to the tz by the probability of z, so fz, and then integrating that across all of the z's that are possible. So you take the function that's written in this spot and you multiply it by the matching density and you integrate them. Is that okay? Which requires me to know what this is. Oh, crap. No, I have to look that one up. I think it is 1 on root 2 pi e to the minus z squared on 2. Sorry? A sigma? Okay, so just a second. I think so the traditional for Z, for n mu sigma squared, did they put a squared in here? Yep. Then the f of Z, the f of Y would be 1 over sigma root 2 pi e to the minus Z minus mu squared on 2 sigma squared. Is that right? Yeah. Okay. And my mu is 0. and my sigma is 1. I'm surprised myself at remembering that, honestly. So that's on. Okay, and so that means that my mzt must be the integral from minus infinity to infinity of e to the tz e to the minus z squared on 2 dz. I'm okay. Sure. And why not? Okay, so yes, I did choose the hardest one. So if we can do this, we can do anything. All right. Oh, crap. I forgot the 1 on root 2 pi. Sorry? No. Well, there is a 1 on root 2 pi, and there is an e to the power of thing with a square in it. That looks remarkably similar. I mean, it's a bit weird, but remarkably similar to the PDF of a normal distribution. So what if I made it look even more like one that was a PDF of a normal distribution? I'm going to fiddle with that exponent. So tz minus z squared on 2. I'm just gonna, there's gonna have to be a 2 on the bottom. So I'm gonna take out the minus a half. And that's gonna give me a z squared minus 2tz. Yep. Is that okay? If I expand this out, it gives me this. Excellent. Now, here we go. Ready? I'm going to complete the square. If there was a 2tz in the middle, that would mean that that would come from a z minus t all squared. So the way when you complete the square, you take this coefficient, you divide it by 2, and you square it, which is what I've got here. Yes, look at that. It's so fun. So this is z minus t squared. Okay, look at that. That's fabulous. I love it so much. So my mzt is now the integral from minus infinity to infinity of 1 on root 2 pi of e to the minus z minus t squared on 2 plus t squared on 2. I'm so happy about this because without this bit here, that is the PDF of a normal distribution with mean t and standard deviation 1. See, look, see, the t is in the spot where the nu goes. So this plus up here becomes a times down here. And this doesn't involve, that's not a dt, sorry, that's a dz. Sorry about that. This doesn't involve a z, so it can come out the front of the integral. And my friends, this is the entire integral of a PDF, which means it's 1. PDF for a normal distribution with mean t and standard deviation 1. Hey, look. Ba, ba, ba. The sigma's 1. Yep, there it is. The mu plays the role of the t. And therefore, it is 1 when you integrate the whole thing, because that's what you get when you integrate an entire PDF. Because if you integrate an entire PDF, you get the probability of everything, which is 1. And so therefore, we have a moment generating function. Yes. Mm-hmm. From here to here. Yep. So when you complete the square, your goal is to write something like this, right? Z plus or minus something squared. So the way I did that is I, in fact, imagined what I was going to do here. And I went, I'm going to have Z minus something because of this minus. And whatever this is, when I expand it out, I'm going to get Z squared minus 2 times Z times this, plus this thing squared. And so therefore, the thing in this spot must be T. And now when I expand that out, I get this. So Z minus T squared is Z squared minus 2Z TZ plus T squared. But comparing this to this, I can't just go adding a T squared. I'm going to have to subtract it as well, so I haven't actually changed anything. And that is how I completed the square. Ah, that works better. Yes, if there hadn't been a 2 there, then this would have been a T on 2, and that would have been a T squared on 4. Yeah, and that would have been bad or worse. And so there it is. And let's just to check, right? Just check. E to the T squared on 2 would be 1 plus T squared on 2 plus T squared on 2 squared on 2 factorial plus T squared on 2 cubed on 3 factorial plus forever, right? Just being absolutely clear on what I'm doing here. And that would be uh 48. So look at this. Ready? The mean okay. So the first moment is 0, and the second moment is 1, and the third moment is 3, and the is 0, and the fourth moment is 3. Anyway, point is, this doesn't have a t term, which means that the expected value of y must be 0. And it doesn't have a t cubed term. If that means the expected value of z cubed is also 0. This proves to me that the expected value of z to the even number is 0 when z is the standard normal distribution, because this Taylor series doesn't have any odd terms. That's so cool. I didn't know that. Yeah.
What happened to the 1 on root 5?
Oh, crapper. No, it's part of this. So the 1 on root 2 pi is part of the PDF.
Why isn't E squared on 2 pi?
Well, I have 1 on root 2 pi times this, and I only removed this, factorized this one out, and left the 1 on root 2 pi behind. It's not a plus here, it's a times. So you times 3 numbers together, right?
No, I understand why you can pull it outside into it. I don't know why
If you were to just.
Oh, you're leaving the PDF of the normal.
Yeah. So the PDF of the normal has the root 2 pi in it. And then when I integrate that entire thing, including the root 2 pi, I get 1.
Gotcha. That makes sense.
Mm.
And my other question
Mm.
was, isn't the variance between the square of the b minus that one?
So the variance of z or y or whatever will be the expected value of z squared minus the expected value of z then squared.
So the first moment is 0,
Yep, which makes this 0.
and then your second moment would be coefficient t squared.
No, it would be the coefficient of t squared divided by so when you wait. There's a 2, you have to factor in the 2 factorial on the bottom.
Okay. And that's 1.
Yeah.
Yeah.
Yes.
Thank
Yep. That's why I arranged for 24 to be here. Technically, this is divided by 3 factorial.
Yeah.
And so that's why I know that the expected value of z cubed is 3. But you could also, if you wanted to, differentiate this enough times, and it would turn into the thing you want. So just to be absolutely clear, the expected value of y squared should be the second derivative of this. Should be m double dash 0, right? So m dashed of t is t e to the t squared on 2, because keep this the same and then times by the derivative of that, which is just 2t divided by 2. And now m double dash t is 1 e t squared on 2 plus t times t e t squared on 2. And so when you sub in 0, m double dash of 0, you get e to the 0 plus 0 times 0 times e to the 0, which is 1. Yay! And so this is the expected value of y squared, which is z squared, sorry. Which is definitely supposed to be 1. So it all works out the way we hope it does. But if I wanted to find that the third moment was 0 by derivatives, it would get progressively worse. But by Taylor series, it's magic. I love it so much, the Taylor series. It's just, yeah, anyway. Like all of these things were kind of invented in the same 100-year period. So, yeah.
Let's try that.
Yeah, that's right. Yeah. So you can do moment generating functions even for a discrete distribution. It works as well. So I'm going to do one more example. Y is, how do you do binomial distribution? Just with a B or with a bin? Like that. Find the moment generating function for Y. And so the moment generating function for Y, which is a function of T, is the expected value of e to the t y. And to do that, well, that's a sum instead. And so that would be the sum from, can't use n, k it is then, from 0 to n of the probability, right, of e to the ty times the probability that y is equal to y. That's how you do it for a discrete distribution. Multiply each thing by its matching probability. And for our thing, probability that y equals y is n choose k, p to the k, 1 minus p to the n minus k. P to the y, 1 minus p to the n minus y. That's the probability mass function of a binomial distribution. Have I got that right? This would be a y, and this could be a y. There we go. That's better. That's better. The world makes more sense again. I've mixed two variables together and I'm not paying attention. Okay. Well, I'm not a fan of this, people. That's okay. It's all right. I'm going to see these both have a power of y, so I'm going to join them together. Is that okay? So this is e to the t, then to the y. This is p to the power of y, so I can kind of factorize out the power of the exponent of y. Nothing up? Yep. No, I'm not going to do that. It's a good idea, but nothing up my sleeves. Are you ready? This is so cool. This is so cool. When you expand out x like a plus b to the n, you get the sum of n choose k, a to the k, b to the n minus k. And that's exactly what I've got, where a is p e to the t and b is 1 minus b. And so this, therefore, myt is the sum from y equals, no, we've already got that, is p e to the t plus 1 minus p to the power of n. Magic! Binomial theorem. Cool. As mentioned in the Pirates of Penzance. It is one of the lines in the Major General's song. Yep. I'm very well acquainted too with matters mathematical. I understand equations both the simple and quadratical. About binomial theorem, I'm brimming with a lot of news, with many cheerful facts about the square of the hypotenuse. Yay! Anyway. So that is that. You may notice that moment generating function proofs tend to use a couple of magic tricks. One of the magic tricks is happening to notice the integral of an entire PDF. And the other one is happening to notice a series that I recognize. I should say to you, there is a handout in the Maths Learning Center, also on the Maths Learning Center website, called Useful Series for Probability, which lists things like this. Yeah. This one's not nearly as pretty as the one for the normal distribution. It's a bit clunkier, but this move is just sweet. It's just, yeah. So there you go. That's moment generating functions. And so this means that I could find the expected value of y squared from this, just to be clear that we're using our moment generating functions correctly. The expected value of y squared. So the expected value of y, we know what that is, it's NP. But the expected value of y squared is m double dashed 0. So my dash t is n p e to the t plus 1 minus p to the n minus 1 times p e to the t because of the chain rule. Yep. And my double dash t is product rule. Okay, the n will still be there. And we'll keep this one. N minus 1. And we'll differentiate this one, which is the same. And then we'll differentiate this one. And keep this one. And then we'll sub in 0. And so I get n p e to the 0 plus 1 minus p n minus 1 times p e to the 0 plus n minus 1 p e to the 0 plus 1 minus p n minus 2 p e to the 0 p e to the 0. And p e to the 0 is 1, and so p plus 1 minus p is 1, and 1 to the power of n minus 1 is 1. And so I've got np here, and this one is n minus 1 times, that's 1 times p squared. And they've both got an np in them. Have I done something wrong? It should be np1 minus p, shouldn't it? No, it shouldn't. That's okay. The world makes sense. That's fine, because I know that the variance of y is the expected value of y squared minus the expected value of y squared, which is np1 plus n minus 1p plus np squared. Yeah. Minus np, right? And that's np 1 plus np minus p minus np, which is np times 1 minus p, which is what it should be. Yeah. Okay, cool. So we did everything right. We checked one of them and it worked out. Cool. Fun, fun, fun. This one, not so fun to just write its Taylor series down. No. Yeah. This could totally be an exam question, right? Oh, is it? Strongly hinted. Does that answer the questions you might have had about moment generating functions? Cool. I don't know any of them off the top of my head. Do you get to take notes? It couldn't hurt if you've got a list of famously helpful distributions to write their moment generating functions down. Yeah. Oh. I mean, if you're going to make a list of distributions for this course, each one should have its mean and its variance and its moment generating function, if you're supposed to know, and a situation in which you are likely to observe it. Oh, yes, and it's PDF and or it's CDF, depending on which one's most useful. Yeah. So you should write down all of those things. Like basically all the ways to recognize one of them that I wrote down earlier, wherever that was. Maybe not the list of moments, but that's the same thing as putting the mean and the standard deviation down. Well, the first couple anyway. Yeah, they should be on the list of things to know about a distribution. That's what I'm saying. Possibly not both of these, but whichever one's the most useful to you. So for example, the exponential distribution, its CDF is much more useful than its PDF. All right, cool. Well, that's that. Where's my list? I've lost my original list of requests. Ah. What's the other one? Okay. Yeah. Finding PDFs of new distributions from old. Those who are listening to this video online, we've had a little bit of people been talking about stuff. Lecturer has said that they've mentioned three methods, which is the moment generating function doesn't generally produce the PDF, right? Oh, then you can find its moment generating function from the other ones. Yeah. Finding and then say, aha, yep, gotcha. Okay. There's three methods. There's the CDF, there's the transformation, and there's moment generating function, which is, a bit dodgy, but I will say something, and something that I'm going to say is that the transformation method is the CDF method. It's a shortcut version of the CDF method. Yep. Yep. So the transformation method is a shortcut version of the CDF method. The reason it works is because of the CDF method. Yes. 100%. Okay. So, let me show you the CDF method and I'll convince you. I will convince you. But I will say this, when you do the CDF method, if you're looking for a PDF, you'll do an integral to find the CDF and then you'll differentiate it to find the PDF. And if you do an integral and then a derivative, you get the original function back. That's why there's no integral in the transformation method. Okay, all right. I only know how to do this through example. And then I can kind of abstract the method. And then I'll be able to try and remember the transformation method. So, I can probably make one up. I'll make one. X is a uniform distribution from 0 to 1, say. And Y is a uniform distribution from 0 to 2. And Z is X plus Y. Is that okay? So do you have a dumb ones like this where you had to find the CDF of the thing that when you add things together? All right. Sadness. I may come back to this, but we won't do that now. Mhm. That's okay. If we can do this, we can do anything. No. Okay, we'll find the PDF of y. Okay. So the CDF method is to first find the CDF of y. So first, so that's the question. And that will be f capital Y of little y. Okay. So the CDF of y is the probability that capital Y is less than or equal to little y. That's what the CDF is. And that would be the probability that 3e to the power of x is less than or equal to little y. Which is the probability that e to the x is less than or equal to y on 3, which is the probability that x is less than or equal to ln of y on 3. Cool. ln is a perfectly good increasing function, and so therefore when I do it on both sides of an inequality, it will still stay the same way round. If I did a decreasing function on both sides, it would flip. You may note that the thing that I just did was to find the inverse of this function. You may notice that. And the probability that x is less than or equal to a number is from the uniform distribution, because x is from a uniform distribution. And so here is the uniform distribution from 0 to 1. This is x, this is f of x, right? And it has height 1, so that the area is 1. Therefore, and if we have this point here, which is ln of y on 3, then the probability that x is less than or equal to ln of y on 3 is ln of y on 3 times 1, because the height is 1, like this area here. As long as ln of y on 3 is between 0 and 1, this will be fine. So f y of y is technically, if you really want to do integrals, it's the integral from 0 to ln of y on 3 of 1 dy, 1 dx. I'm just going to stick in the previous lines of working. Fy of y was the probability that x is less than or equal to ln of y on 3. Which is just ln of y on 3. Okay. And so therefore, little fy of y will be the derivative of this, which will be 1 on y on 3 times the derivative of the inside, which is 1 on y. Yay! I should probably be really careful about what the values of y that are possible are. Yeah, so at this point, this will only be true if ln of y on 3 is between 0 and 1, which is basically comes out to this being between 3 and 3e. So just going to go back here. If x is between 0 and 1, then e to the 3e to the x is between 3e to the 0 and 3e to the 1. So that's between 3 and 3e. And so my fy of y is 1 on y when y is between 3 and 3e, and 0 otherwise. Yeah. Okay, so this one was pretty easy from after the point where we created our integral, because we didn't have to integrate something fancy because it was just the number 1. But notice some things. In this process, this is the inverse of that function. I did it by unwrapping this to get back to x, which is what the inverse function is for. And I created my integral of the original function's PDF here. That's what's in this spot. And then I subbed into that the original, I subbed into that f inverse, like h inverse, and then I differentiated that. So when you do the transformation method, I am almost certain that it's going to be, I'm going to let h of x be 3e to the x, right? And h inverse of x is y, h inverse of y is ln of y on 3. Because I have to first divide by the 3 and then do the ln. And h inverse dashed of y is 1 on y on 3 times 1 on 3, which is 1 on y. And to do the transformation method, I'm almost certain that we will have that little f y of y will be fx of h inverse of x. No, wait. H inverse of y times h inverse dashed of y. Yep. Where's the absolute? Okay. And so in that case, we get 1, because fx is just 1 no matter what you put into it. And this is, yeah, it's very 1 on y, but y was positive anyway, and so that's not a problem. 1 on y. Okay. So the transformation method is a shortcut that deals with the fact that you're going to sub in your, yeah. So it all works out the same as the CDF method anyway. And what we're doing is we're skipping the bit where we did the integral and then the derivative. Yeah, there are some technical details where some years they talk about what to do if your original function isn't 1-to-1. Do they do that this year? Nope. Okay, then don't worry about that then, because it can be dealt with.
Yes.
Monotonic. So he does say what to do when it's not.
So if it's increasing part of the region, then increasing the other, or vice versa, then you split at the point where it switches and do it separately, and then
And so the interesting and confusing bit of that is that you actually add them together. You don't get a different f of x for one bit and another f of y for the other bit. You, in fact, f of y for the entire thing is what you get when you add them, which I think is always puzzling. And there was a year when I figured out why that was true, but I don't know if I'll be able to do it again. Yeah. So you're really sure you haven't done ones where you had to add them together because there's like a multivariable integral? Oh. Let me see. That one was increasing and decreasing. Oh. So this is the same. This is the one that everyone's talking about where you split it into two pieces, right? It's split into two pieces and you got these two things. Yeah, and then you've literally added them. Okay. I was. Oh, interesting. Yeah, but that's not what it's. So this order statistics bit, right? Yep. Is technically a multivariable thing. I see something very interesting in the work. I'm going to do the example I was going to do anyway, because I want to show you something. All right. X is going to be something from 0 to 1. Y is going to be uniform distribution from, yeah, let's do from 0 to 2. And Z is going to be X plus Y. So we randomly pick a number between 0 and 1. And we randomly pick a number from 1 to 2. From 0 to 2. And we add them together and we get Z. Okay. And I can in fact do the PDF of Z from this information. So this is these are linked distribution. Like this Z is, yeah, it's a two variable sort of thing. So these are the X's from 0 to 1. These are the Y's from 0 to 2. And these are all of the values of X and Y that are possible, the combined values of X and Y. And Z will be the sum of those two values. I may have made myself a really bad problem, but that's okay. So if I want the CDF of Z, then it is the probability that Z is less than or equal to little z. Okay, that's how you always do a PDF. And this is the probability that X plus Y is less than or equal to little z. And X plus Y being less than or equal to little z would be a line like, it's equal to little z would be a line like that. That crosses z here and z here. That line is X plus Y equals little z. And so if Z is less than 1, then we've got a little triangle here. And if Z is is more than 1, then we've got a little trapezium here. And if Z is more than 2, we've got a little rectangle minus a triangle. And I'm going to say they're independent. They're independent of each other. So if they're independent, then every possible combination is the same probability, basically. And so what that means is that if Z is less than or equal to 1, I've got the probability that X plus Y is less than or equal to Z is this area that's half of Z squared. That's this thing here. Technically, it's that area times probability of X and probability of Y. And if Z is between 1 and 2, then it's this area, which looks like it is, it's definitely Z high on this bit. What area is that? I guess this would be because that's slope minus 1. This distance is 1. Okay. And so this height is Z minus 1. So we've got half of Z squared plus Z minus 1 times 1. That's this area here. And then when Z is in the top corner, this was a bad example. Sorry, everybody. We get whatever we get. This is a bad example. Sorry, guys. Whatever that area is, an answer. I'm going to stop there. And so my CDF is zero. If Z is before 1, is less than 0. Half of Z squared if Z is between 0 and 1. Half of Z squared plus Z minus 1 if Z is between 1 and 2. Answer if Z is between 2 and whatever the last final point is, and 0 when Z is more than that final point. So all I was saying, that's all I was trying to say, is that it's totally possible to figure out what happens when you combine random variables together. That's all I was trying to say. That was a bad example, and I'm very sorry about that. But I will say, what if X and Y were from a uniform distribution 0, 1, right? Independently, and Z is the maximum of X and Y. That is an example that you've been given. And so then you're saying that the Fz of little z is the probability that big Z is less than or equal to little z, which is the probability that the maximum of X and Y is less than or equal to little z. And for the maximum to be less than a number, both of them would have to be less than that number. So that's the same as both X and Y are less than or equal to Z, which is the probability of X being less than or equal to Z and Y being less than or equal to Z. And because they are independent, it's that. Can I change this back to my original and make them different? Yeah. And so x is these things from 0 to 1 with height 1. And y is these things from 0 to 2 of height half, because the total area has to still be 1. And so the probability of being less than or equal to x, z for x would just be z, if z was in this spot here. But for y, it would be this area here. So if z is between 0 and 1, the probability of x being less than or equal to z is z, and the probability of y being less than or equal to z would be z times a half, because of this diagram here. But if z was between 0 and 2, probability of x being less than or equal to z would be 1, because we've already gone past the end. And the probability of y being less than or equal to z would still be half of z. And so we've got that f z of z is z times half of z, so half of z squared. And this one is just half of z. So this is when z is between 0 and 1. And this is when z is greater between 1 and 2. And so what that means is that little f z of z is z when z is between 0 and 1, because I differentiated that, and a half when z is between 1 and 2. But most of the time, they give you the same distribution for both of them. But I just wanted to show it was possible. Yeah. So most of the time, what they actually give you is something like y is distributed as y1 and y2 and y3, etc., up to yn are distributed as a normal distribution with mean in 0, 1. And then you have that y is the maximum of all the yi's. And then you go, well, okay, fy of little y is the probability that big Y is less than or equal to little y, which is the probability that the maximum of all of the yi's is less than or equal to little y, which is the probability that y1 is less than or equal to little y, and y2 is less than or equal to little y, and all the way up to yn is less than or equal to little y. And so that is y1 is less than or equal to little y times, because they're independent. They're independent, I didn't say that. And that is capital F of yi, of little y, to the power of n. And so therefore, little fy of little y will be n with that. I shouldn't have done normal distributions because there is no formula for its CDF. So I should have done something else. Made them exponential distributions or something. Something like that. Because then the CDF is 1 minus e to the lambda y, I believe, for the exponential. Pretty sure. Minus y. Yep, that's right. And then this is lambda e to the minus lambda y. Yeah. Cool. So this is in the chapter called order statistics. And so you can do it for the minimum as well, but it's easier to go. So if it's the minimum, everything has to be greater than that number if the minimum's that. And so all of your things are 1 minus the f of capital F. Yeah. So there are totally things that can happen. I'm worried that these don't match up, but that's okay. That's okay. Totally okay for a PDF to have a jump in it. Right. So yeah, in my head, the CDF method is the gold standard because you can always use the CDF method. But the transformation method has that extra spice where you can think about what happens if your function changes direction partway. But yes, I tend to use the CDF method to help me remember the transformation method. Yeah. Okay, I think that'll do. Thank you so much for coming. I will just stop the recording. Actually, no. For those who are still at Uni of Adelaide, it's still 2025. Math Learning Centre is open all the way until the end of the exam period. But when the exams start, we from this week it's 10 a.m. to 4 p.m. Monday to Friday, but when the exams start, it's 1 p.m. to 4 p.m. Monday to Friday. You can be there before 1, but we won't. So cool. Now I'll stop the recording.